Okay, now we want to talk about the critical mass energy density of the universe. So first we need to define what is density. So density is given by the letter rho, and it's going to be equal to mass divided by volume. So that's your general definition of what density is. But if we want to talk about the density of the universe, we also have to include the energy of the universe, because according to Einstein, energy is equal to mc squared. So that since the universe has energy, the universe has mass, and so therefore we really need to talk about the mass energy density of the universe. So then the next thing would be, what would be the critical mass energy density? So this would be a specific density that would be required in order to stop the expansion of the universe. So according to Hubble, the universe is expanding. And so if there was enough mass in the universe, that would cause enough gravity to start to slow down the expansion of the universe and possibly stop the expansion. And so that amount of mass and energy is going to be called the critical mass energy density. Now, the value of the critical mass energy density can actually be calculated by using Hubble's law. And so we have then that the rho critical is going to be equal to, and it's going to be 3 times Hubble's constant, but you need to square it, and then divided by 8, and then pi, and then big G. So notice that it depends on gravity. So gravity is what's going to be trying to pull the universe in, and then Hubble's constant is the thing that is related to the expansion of the universe. So you've got these two competing things, gravity trying to pull the universe in, Hubble's constant trying to push the universe out, and then the two of them put together determines what the critical density of the universe has to be. So we can plug in the current accepted value for Hubble's constant, which is 22 kilometers per second per mega light year, and then plug in the current value for the gravitational constant, and then we end up with a critical density of 8 times 10 to the negative 27th kilograms per cubic meter. And so this is equivalent to 4 hydrogen atoms for every cubic meter of the universe, which is not a whole lot. And so to compare that, the density of the air in the room where you're at right now is 1.204 kilograms per cubic meter. So that the air in your room is much, much, much more dense than the density of the universe as a whole. And then it's kind of interesting that the actual mass energy density of the universe is within 0.5% of this critical density, but it's not quite enough. So we think that the actual mass energy density of the universe is just a tiny bit less than this critical mass energy density. And so that would mean that the universe is going to continue to expand forever. All right, let's take a break. When we come back, we're going to talk about general relativity.